Where cardiovascular cells may be likened to a roller coaster, potential action coast system, the lymph system is much more like a lazy river. Lymph vessels have no pumping system. Instead, they rely on the gentle rhythmic flow of the body to slowly propel the lymph through the body. The slow flow of the lymph moves through the vessels based on surrounding tissue movement. The more someone moves around, the better able these vessels are equipped to propel the fluid up to the thoracic ducts, into the cardiovascular system through drainage into the subclavian veins. The valve network in the lymph vessels is a pressure-dependent system which relies on pressure rather than gravity to propel fluid. As pressure from surrounding tissue or in other enclosed vessel compartments increases, the valves open to allow the lymph to flow into the vessels. Leakage from blood vessels into the interstitial spaces collected by the lymph vessels, 2 liters or more a day, is collected by the lymph system and filtered through its networks before returning to the cardiovascular system. The highly flexible nature of the lymph vessels allows for more fluid to remain in these vessels, and as fluid collects can be problematic to the body, leading to lymphedema. The nerves present in the adventitia of the lymph vessels are theorized to have a number of effects on the vessels themselves, but this has been a vastly understudied concept. It has been observed through numerous studies, however, contractile capabilities of lymph vessels with the presence of norepinephrine, noradrenaline, and stimulation in these nerve fibers. In the lymphatic vessels, lymphocytes and macrophages flow lazily through. When they travel to various locations, monocytes will further differentiate into macrophages and/or dendritic cells. In lymph, macrophages are abundant in the fluid. Macrophages are a phagocytic cell. Phagocytosis is the consumption of cellular bodies. To be phagocytic means the macrophage is capable of eating other bodies. Their role in the immune system allows initial attempts to consume a pathogen or antigen, as well as carry the pathogen to more specialized to promote further immune responses. The journey of an antigen-carrying macrophage is normally to central lymph sites known as lymph nodes. Both lymph and blood flow into the lymph nodes to undergo a preliminary filtration process where antigens are consumed and B cells activated, which differentiate into plasma cells and produce immunoglobulin G, IgG, antibodies. The density of immune cells in these locations are what drives cells to carry antigens from the bloodstream into the lymph nodes for further decommission by the lymphatic system and production of immune responses. Cells and dendritic cells travel through the bloodstream and carry antigens to the surface of B cells inside of our lymph nodes. Most differentiation is stated by cytokine reactions, which help the hematopoietic stem cells determine what cells are needed in the body. Erythropoietin, a kidney-derived hormone, helps to stimulate the hematopoietic selection, but hematopoiesis is largely dependent on the numerous chemicals throughout the body and not solely influenced by erythropoietin. T cells form in bone marrow as hematopoietic stem cells and mature in the thymus and are integral to the adaptive immune system, our body's first immune responder. T cells are differentiated into T helper cells, which promote cytokine immune helping responses, killer T cells, which initiate cytotoxic responses against viruses and tumors, memory T cells, which help develop and remember antigen exposures for quicker future immune responses, regulatory T cells, which modulate and end cell immune responses. Additional T cells are developed, but these are the primary T cells of interest. T cells are in heavy supply in lymphatic structures, but are free-flowing in the bloodstream as well. The hormones thymopoietin and thymidine help the differentiation process. Thymus is a very active immune supportive organ in adolescence that begins to lose its function in puberty when its tissue begins to be replaced by adipose tissue. As we age, the thymus will lose all of its T cell differentiation abilities, truly highlighting the importance of immune development in adolescence. The thymus also produces the hormone thymosin, which stimulates T cell production, matures B cells to plasma, and stimulates some pituitary hormone production. Thymic humoral factor is created in response to viral-specific exposures and carries out the same function as thymosin. In homeostatic functions, the small tonsillar tissues play a large role in ensuring the body is equipped in dealing with new introductions of foreign invaders. These tissues begin reading foreign substances and creating immune responses based on the pathogen derived from M cells that create the initial response. A great deal of the inhaled irritants are collected by the palatine tonsils, which store the bacteria in crypts located within the tissue. Mucus production is ramped up by the tonsil tissue during pathogen exposure and creates an additional net to catch the pathogens and expel out of the body. The tonsils create a lymphokine and immunoglobulin response locally based on M cell signals, which activates B cells and T cells to create the immune response. B cells will further create a memory of the pathogen and use for future exposures. In utero, the spleen plays a primary role in developing blood cells as a precursor to bone marrow development. At about 25 weeks, gestation takes this role in developing blood. Spleen's primary function postpartum is to break down platelets and filter blood. The structure of the vessels in the spleen allow for both healthy blood cells to pass through and aged, irregular-shaped blood cells to become trapped, where they will be broken down by macrophages. The structure is also highly flexible and provides a secondary source of stored blood and nutrients to supply the body in the event it needs to have additional blood supplied. The amount of lymphocytes in relation to its small size is also remarkable, considering the spleen stores a quarter of the body's lymphocytes in this tiny, mighty organ. The vascular networks of the bone help to carry blood to the bones, as well as carry mesenchymal and hematopoietic cells out of the bones. The red marrow contains hematopoietic stem cells, which produces hematopoietic, a precursor for myeloid and lymphoid cells, as described earlier. The cells then travel to various locations in the body where they mature. The appendix is theorized to be a storage site for good bacteria to aid in gut microbe depletion. However, little functional purpose is known about this organ. The appendix has an identical structural anatomy as the Peyer's patches in the small intestine. Peyer's patches contain no afferent lymph supply, but instead perform some lymphatic functions through T-cell mediation in the patches and B cells inside the germinal centers, and contains efferent vessels for further antigen processing and antibody development in larger lymphatic organs. Ingested pathogens activate immune responses via the Peyer's patches, in addition or as a replacement to tonsillar organs. Lymphatic tissue is supportive to all systems in the body and works closely with the vascular system to receive and give cells to the blood system. Though the only primary lymphatic organs are considered to be the thymus and bone marrow, where T-cell production and maturation occurs, the other structures mentioned perform secondary immune responses supported by the lymphatic system. The lymphatic system as a whole works congruently to protect our body from foreign invaders.